Everyone's heard the narrative that AI is this black box, and that is true. Nobody fully understands what's going on, but I would argue that by studying the algorithms that power these things, we can learn some intuition about what's actually happening. So today we're going to be studying the forward pass, and that'll hopefully give you a solid foundation that you can build a deeper intuition of what's going on with these models. The story starts in 2017 with the invention of the transformer architecture by Google. In this paper, attention is all you need. And so the big breakthrough here was the using this thing called multi-head self-attention, which kind of has proven itself to be this general purpose algorithm for sequence processing. And another big aspect of why this thing has made such a splash is because of how well it's suited for the hardware that people train models on. So GPUs are great at parallelization, and previous language model architectures were sequential. And so while in theory they were powerful, in practice they were hard to train because they didn't match the GPU paradigm well. So this innovation allowed bigger models to be trained faster. And so then the next year, OpenAI created the GPT, a generative pre-trained transformer. And so they pretty much took the transformer from this Google paper, but then what they did new was what they called generative pre-training. So they did huge scale unsupervised learning on a bunch of text. And at the end, pretty much they had this model that had learned general truths about language. And so that essentially gave them the single foundational model that they were then able to fine tune for a wide variety of tasks downstream, leveraging like it had learned a bunch of things about language. So, we're going to be talking about what happens when we're running inference on these things. We're not going to be talking about the pre training process. We're talking about, okay, I have this pre trained model, I invoke it, what happens? And we're going to be using GPT-1, that first model, because it's an interesting relic of history, as well as being simple enough that it's easiest to understand, but its skeleton, the core piece of how it works, is still the same thing you see today in all of the descendants, all the LLMs that we know and love. So we're going to be talking about the input, tokens, and embeddings, both token and positional. We're going to be talking about the processing that happens in the transformer blocks with that multi-head self-attention algorithm, as well as a multi-layer perceptron. And then we're going to be talking about the idea of a residual stream, which is essentially the memory of a transformer and why that's so powerful. And then we're going to be talking about in the output stage, unembedding, and then sampling. This diagram shows what's going to happen when we actually invoke our GPT model. So first of all, we need to run a tokenizer. We can convert text into something that the model understands. So that's like our input stage. And then processing stage here, we're going to run, this is the multi-head self-attention, and then this is that multi-layer perceptron. And so important things I want to talk about here are how these are multiple attention heads and they're all reading from the same source. So this is the residual stream. And we can see that each head is getting a different slice of the input, and then it's doing its own processing. And then each head adds its output back onto the residual stream. And then from there, the multi-layer perceptron is going to read from the residual stream, do further processing, and then it's going to add back to the residual stream again. And so this example only shows one transformer block, but in reality, you would have a stack of these things, and the residual stream carries all the way through. And so that's pretty cool that everything is additive because it means that the residual stream is effectively the memory of the model. So layer one can write something to the residual stream, and then layer 10 can read from there, do more processing, and then effectively like leveraging what layer one did. And then eventually, once we've run through all of our transformer blocks, we want to actually go back into the land of text. And so we unembed, and then we have like our logits, and then we're gonna convert things into a probability distribution. So our model is actually producing a probability distribution of the next most likely token for all of the tokens that it knows. So here, hello world, you know, the most likely next token is probably some type of punctuation, but this would be actually as tall as the model's vocabulary size. This is some math from the GPT-1 paper. And so you can see they've broken it down into 3 different steps. And we're going to start here with H0. So in this context, H refers to hidden state. And so I've got a Python notebook here that we're going to use to kind of walk through what's going on. So just doing some imports, some things from the standard library, PyTorch. Notably, we're pulling in GPT and Tokenizer. So these are the model and the tokenizer respectively from the Hugging Face Transformers implementation. And then we're pulling in some other helpers and stuff. And so we can display what the model actually contains. This is everything that will touch the input when you invoke it. So we can see here that there are tokens embed, positions embed, there's drop, and then there's H. So that's referring to all of the hidden states that we have. So you can see there are 12 of them in GPT-1, 12 transformer blocks, each one having a tension, a layer norm, and then a multi-layer perceptron, and then another layer norm. And then eventually this LM head, so that's that that output stage. And so there are things in here that are important but boring. And so like I would classify dropout and layer norms in that category of they are pieces of the algorithm that are required to make this thing work well, but I don't think that they're as important for gaining the intuition of the algorithm. So I'm going to be kind of glossing over those pieces. But to start with, neural networks deal in numbers, not human language. And so we need some means of translating from human language into something the model can understand. And so that's where tokens come in. So if we display our tokenizer, we can see OpenAI GPT tokenizer, and then notably it has a vocabulary size of 40,478. So a tokenizer has a vocabulary. This thing is a function that pretty much you feed it a corpus of text, and then it runs some like statistical stuff to figure out the most frequently occurring units of language within a corpus of text. And so this tokenizer has already had that happen. And so there are 40,000 units of text that it knows and can turn things into. So got this helper show token mapping. So we're going to be going from tokens to their IDs, passing the tokenizer to do so. And then this is our string that we're going to tokenize. So running that, we can see, as I've noted, tokenizers convert text to integer IDs. And so like words are broken into subwords, and sometimes they're the full word. Sometimes they are pieces of punctuation like that. Numbers are weird. But yeah, so pretty much we can see that each unit of text is associated with a number ID. And so that number ID is really how the model learns um, what to associate with a representation. And so we mentioned it has like that 40,478 vocabulary size. So going the other way now, we can just look at different parts of that space that the tokenizer knows, its vocabulary. And so notably here, there's this like unknown token. So if you feed it some type of text that is not within its vocabulary, it's going to get cast to this unknown. So maybe like an emoji or something like that. Um, and yeah, sometimes a single letter is considered a token. Sometimes they're full words. If we look at um, the tokens embed from our model, you can see that it's this embedding layer, and as an input dimension, it has that 40,000 number. So that matches exactly our tokenizer vocabulary, and that is no accident. The tokenizer and the model need to have the exact same vocabulary because that tokenizers are translation piece. And so that's how the model um, knows what piece of text that we're talking about. And then this 768 number, that is something that you'll see called D model, the dimension of the model. And so 768 here is the dimension of our embedding. So we'll talk about embedding shortly, but I also want to talk about how there are these positions embed, and rather than the 40,000, it's 512. And so what this means is that GPT-1 has 512 unique slots that tokens can fill. And so you may recognize that as the idea of a context window. And so notably, it has so many number of slots positionally, but it has the same dimension of the embedding. So both tokens and positional embeddings are represented in the same number of dimensions. So embeddings are pretty much the mathematical representation of language in a way that is meaningful. And so I think that this example from Word2Vec, which is a paper and model that predates transformers, but this was pretty groundbreaking at the time. They trained this model that learned language, and so they ended up with these word embeddings where they were able to do word math. They took king minus man plus woman, and then that took them to the vector that most closely matched to queen. So here we can see like this is our vector representational space, and if we start at king and then we subtract man, so that's this arrow, and then we go to where woman exists, we can add that blue arrow, and then that takes us to where queen is. And so this is to demonstrate that like these things are learned representations where magnitude, or like how long a vector is, and the direction that it's pointing are meaningful in a way that is semantic. So embeddings are things that are learned. We start with them being randomly initialized, and then through the training process, they like find their way to a location in this vector space that has rich semantic meaning. So if we look at a given example of an embedding, so 3001, that maps to shock. If we look at the token embedding for shock, we can see firstly that it is a vector of 768 dimensions. And then when we look at it, it's a bunch of floating point numbers. And so this is obviously entirely meaningless to me, but this is the best representation that GPT-1 has learned to represent the token shock. And so getting back to our hidden state 0, I want to run a piece of text through our tokenizer, and then we're going to return those as PyTorch tensors and look at the input IDs on there and the shape of that. So our tokenizer converted this into 3 tokens, and that's 1, 2, 3. And the shape of our output here is 1 by 3. So you can think of this as like a batch. So we have one batch because there's one piece of text that we're tokenizing. And then there are 3 tokens in this batch. So looking at this piece of math from the GPT-1 paper, you can see this U is meant to represent our context. So what we're passing into the model. So in our example here, it's going to be this tensor where it's that 1 by 3 shape and contains these elements. And so we're multiplying that by the token embedding matrix. And so I think a very fair question is like, well, what is a matrix multiply doing there? How does that actually grab that correct embeddings that we want for those tokens? So I have this example embedding table that is obviously just for demo purposes. We have 5 rows by 10 columns each. And so let's say that I want to grab the 10s, the 30s, and the 50s. So in a normal like imperative programming paradigm, I could just easily say, okay, give me the 0th element here, the 2nd element, and then the 4th element. And so we can solve the problem the same way using a matrix multiply by framing the problem in terms of what are called one-hot encodings. And so you can see here, I've got this token indices where we have 3 elements where each element has 5 things in it. And you can imagine looking at this, we can pivot our 5, and then we like are in this shape, and we're saying, okay, the 1 on the first row, that means give me the first row. And then the 1 on the 3rd thing is going to give us these. And then the last one is going to give us these. So that is cool because it shows that we can kind of think of matrix multiplication as this like function application. So if you don't have like a math background, then I feel like this is a more intuitive way for people with like programming experience to think about what's happening in a matrix multiplication. And so a matrix multiply, the shape of our operation matters a lot. And so we have this 3 by 5 thing, and then we're multiplying it by 5 by 10. And so our inner dimensions need to match, and then the result takes on the first shape from the first thing, and then the second shape thing from the second. So we end up with this 3 by 10 column situation. So to tie it back to our actual hidden state 0 at hand, we kind of talked about like, okay, I can multiply these IDs by my embedding matrix to get the things that I care about. But then we haven't touched on this positional embedding matrix yet. And so let's take a look at, we're using the same tokens that we had up above and kind of printing a bunch of different things here. So let's print this and then step through it. So our input IDs, we talked about this, the shape and then the values there. But then there's this idea of position IDs as well. And so this is the same concept as what's happening in the token IDs, except rather than, you know, correlating to a piece of text, now we're correlating to a position in our context window. And so because we have 3 elements in our tensor, we are going to have position IDs 0, 1, and 2. So essentially we're saying, okay, we have these 512 slots that we can fill. We have 0, 1, and 2. And then with that, that gives us what we need to actually access the embedding matrices. So we can get the input embeds by invoking like our tokens embedding matrix with our input IDs, these things. And then we can do the same with our positions embed with the position IDs. And so at that point, our input embeds is going to be 1 by 3 by 768 dimensions. So that's saying we have our collection, one batch of 3 tokens, and they're each represented with 768 dimensions. And then the same is true for the position embeddings. And you'll notice here that we're saying hidden state 0 is the addition of the embedding matrix plus the positional matrix. And so to get our hidden state 0, we just add these 2 tensors together, and then that is our hidden state. So you can see it's the same size, and we've just added these 2 things together. And so effectively, what this hidden state 0 is saying is like, okay, I have some language. I have learned representation for those pieces of language. Let me grab those. And then I know what different positional, I know what the different positions in my context window mean. So let me combine my language meaning with my positional meaning, and then I have a richer understanding that I can represent that way. So I do wish that they wrote this differently because we can see how we're able to grab the correct token embeddings based on our context. But there's nothing here showing how we're getting the correct positional IDs. But just know that this was written with the assumption that we're filling the entire context window. So it was deemed like insignificant, I guess, but understand that we are doing the same thing for both token and positional embeddings. We're grabbing the embedding representations that we care about, and then we're adding them together, and then that is our first hidden state. Now we have translated our text into something that the model knows how to work with. That's going to take us to the second piece here. So they have identified hidden state L as we're running the transformer block with the output of the previous hidden state. So let's say we're talking about hidden state 1 for now. We're going to run the transformer block over hidden state 0. And so what this other stuff is saying is that for all I from 1 to n, so we know that there are 12 transformer blocks in GPT-1, so n is 12 there. And so pretty much we're saying For each of those transformer blocks, just run it on the output of the previous hidden state. So let's dive into what this transformer block computation is actually doing. And so I have kind of sketched out some pseudocode. As I mentioned, those important but boring things I'm going to gloss over. So we're importing PyTorch, and then this other cool library called inops, which makes tensor operations more readable. And so we're defining some constants. So we have our dimension model at 768, like we talked about, our vocab and context size. And then we have 12 transformer blocks, so 12 layers. And remember that our transformer blocks have multi-head attention. And so GPT-1, each block has 12 attention heads. And so each attention head is looking at a different slice of the input. And so to find the dimension that each attention head is going to look at, we just take our 768 divided by the number of attention heads. So let us start by looking at the transformer block code. So we have a self-attention layer, and then we have a multi-layer perceptron layer. And if we look at the forward, so this is what's going to happen when this is the code that's going to run when we invoke this module. So it's going to take in the residual stream. And so for instance, like our first transformer block, that's going to take in hidden state 0. And then we're going to get the attention output by running our self.attention on our residual stream. And then we're going to add the residual stream and the attention output. And then we're going to consider that the new residual stream. And so important here, like I want to stress that the residual stream is important because it allows the different pieces of the model to talk to each other by writing to different subspaces of this residual stream. And so the same thing happens with the multi-layer perceptron. We run that over the residual stream, and then we add those things together, and then eventually we're going to return the residual stream. So let us now step into some diagrams that I've created. So in this example, I've created a situation where there are 4 tokens with our one batch, and these embeddings are supposed to have dimension 8 as represented by 8 slices on a corresponding rectangle, and the color is supposed to have some meaning. And so the first thing that's going to happen in our multi-head attention algorithm is we are going to pull off from the residual stream into K, Q, and V. So that is shorthand for queries, keys, and values, language that comes from information retrieval. And so what I want to stress here is like we're pulling from the same source, but we're actually doing a linear projection. So despite having the same source, K, Q, and V are all going to be a little bit different, and that's a learned thing. But they'll be storing references to their version of the same source, that residual stream. And then, we're talking about multi-head attention, so I've tried to visualize what that means by having 2 attention heads here. So you'll notice like this black box, we're looking at a slice of our original input just for dimensions now, but it cuts across the entire input. So this attention head gets to see all of our tokens. It's just looking at a different sliver of their embeddings. And then the same is true for this pink box. So each head is looking at a different sliver of our representation. And so let's now step back into our pseudocode and look at the attention class. So I mentioned that queries, keys, and values are derived via a linear projection. So these are things that are learned. And then there's a similar projection that we'll talk about in a moment. And we're also storing a softmax function. And so when we run the forward on our attention module, we're taking in the residual stream again. And that's going to come in that shape of batch tokens and then demodel. And so we're projecting from the residual stream by calling our corresponding linear layers. And so importantly, the shape of all of these things will not change. It's going to match the residual stream. And then because we are doing multi-head attention, we need to split into however many heads we have. And so for our case, that's 12. And so for queries, keys, and values, we run the same operation of we want to go from batch tokens demodel, and then we want to end up in this batch in heads tokens d head situation. So stepping back here, essentially we're saying we have this input, we want to reframe how we're looking at it so that each head is looking at the right spot. And so this is just a INOP syntax where we're essentially saying, okay, we have these 3 dimensions. I want to unpack these 2 things. And then I'm saying what my desired in heads and d heads are. And so after this, our Q value is going to be this shape. And the same for keys and values. And so now we have those things, but what do they actually do? We want to compute what they call the attention score. And so in order to have a valid matrix multiplication shape, we need to rearrange K. So ultimately, we want to have our queries multiplied by our keys that are transposed. And so we do a similar thing here where we're rearranging to transpose so that our keys is now transposed. And then we calculate our attention scores by multiplying here like this, and we end up with the shape batch in heads and importantly tokens by tokens. And so stepping back into the diagram here, these are fake values, but this is kind of what is happening. So we have our token by token grid or matrix. And so pretty much what is supposed to happen in this attention calculation of score is each token gets to look at all the other tokens and then contextualize itself in terms of the context that surrounds it. And so notably there's this like concept of causal masking. So pretty much a GPT model goes one word at a time, one token at a time. And so it would be cheating if it were able to see what came next. And so for each token, it only gets to see like what has come so far. So we mask that out. And so essentially like what this is supposed to be showing is like, okay, at this point, this he token has not, it's the first thing, so nothing else is visible. And so it should retain all of its identity. Its embedding is going to stay the same. But then we get to the low token, and so, it can look back and see this he token, and then it's able to contextualize its representation in terms of um, that he token as well. So, you know, low maybe has some meaning by itself, but when it sees he, it knows, okay, I should retain 30% of my representational identity, but maybe I'll take on 70% of this he token. And so that like merging of representations across tokens is really the key thing that is happening when we're doing this queries multiplied by keys. And so the same thing happens for every token. And so this is very important. For our example here, we're just looking at like a 4x4 token matrix, but today's models, some of the bigger ones have like 1 million context window. And so what that means is quite literally of all million tokens, this calculation is happening. So you have a million by a million grid where you have this situation where there is no bias built into the position of where things are. Every token is going to be able to see every token that has come so far. And so if we're on the millionth token, it's going to look back at every single token that has come before it. And so attention is not a cheap algorithm, but it's very expressive because it's able to handle those very long range dependencies and contextualize in terms of everything that has come before it. So that is the attention score situation. And then now we're going to do that causal mask thing that I talked about to zero out what hasn't been revealed yet. And so in our diagram, these were in like percentages basically. And so we need to do the math to make that actually happen. So we're just going to take our attention scores and then scale them. And then we're going to run our softmax function over that. And so a softmax function takes in a vector, and then it's going to output a probability distribution. And so then we can multiply our our scaled and percentage based attention scores by our values. And so going back here, what that looks like is like we had our value projection, and now we have calculated how much each token should merge itself in terms of the context. And so we multiply these attention scores by the values, and then we end up with a tensor that is reflective of the context. So we figured out how much they should merge, and then we multiplied them by kind of the more raw thing, and then we end up with a better representation because each token is able to merge its representation with the representations of the tokens that came before it. And so that's what we're doing here. And so in the real code, we're doing multiple attention heads. And so we need to combine them. So essentially, how we do that is we just start by rearranging things. Essentially, we are concatenating each attention head scores or like outputs. And then once we have those all concatenated, we're running through another projection. And so that projection effectively has learned to stir all of the attention heads insights into one. So each attention head is kind of um, identifying a different piece of information or value from our input, and then when we combine them together, we have this rich representation that reflects the context well. And so then, like I mentioned here, that is going to be the residual stream after the attention mechanism. And so going back here, that we've calculated our attention output, and now we're going to add it back onto the residual stream. And then we're going to run our multi-layer perceptron over the residual stream. And so the multi-layer perceptron is just a kind of standard feed-forward network. Notably here, we have two linear layers and then a nonlinearity function. And so we're starting with our dimension model, 768, and then the output dimension of this layer is 4 times that. And so pretty much, 768 dimensions is a lot. You can represent a good amount there, but you can represent more if you have a higher dimensional space. And so we can like take our representation space and then blow it into a higher dimension where there's essentially more room for things to be represented. And then we run our nonlinearity over there, and then we do the opposite, where we're going from that high dimension, condensing the work that happened back into our D model size. And so here I've attempted to visualize like, okay, we ran our attention and our multi-layer perceptron. What did the multi-layer perceptron actually do? And I've just added like these white and black slivers here to visualize that we are mutating the information that's on these tokens, but the same function is run across each token. And so like that is why each token representation has had the same modification happen to it. So the multi-layer perceptron's job is to take these tokens and then refine their representations by mutating them somehow. And so then that is going to happen many times, as many times as transform blocks we have. So back to our GPT-1 math, we've discussed the hidden states that involve the transformer blocks, and then eventually we're going to have processed all of those blocks, and that'll be hidden state in the final hidden state. And so then that brings us to here. So the probability, this is probability distribution over U, where U is the next token. And so that is calculated here. And let's talk a little bit about what's happening there. So we're importing similar things. And I've got this little example where, let's say our vocabulary is just these 5 letters. And then our logits are going to be this piece of computation right here is we have our hidden state in, so that's going to be in 768 dimensions. And then our token embedding matrix is going to be the vocabulary size by the D model, so 768. And so if we transpose our token embedding matrix and then we multiply our final hidden state by that, then we effectively are outputting a score for each token in the model's vocabulary. And so that's called a logit. And so in our example, there are 5 vocabularies, 5 things in the vocabulary, so we have 5 logits, 1 score per token in the vocab. And so then we're just running a softmax over that. So like we talked about, that's going to give us a probability distribution. And so you can see that the higher the logit score, the higher the probability. And so that is how we end up with our probability distribution over U. So that is what the model is actually outputting. But ultimately, we care about um, actually selecting a next token from that probability distribution. So if we have some text, we're going to kind of connect some of the dots here. We've going to run our tokenizer over that, and then we're going to run our GPT model, passing the inputs in. And then ultimately, what we care about is the next token prediction. And so the transformer is actually going to, for each token in the context window, predict the probability distribution of the next token. But we only care about the prediction that comes as the last token. So by that, I mean we have our like we had our 4 tokens, but we only actually care about the scores that come out of that final thing, that URLed in this case. And so we're going to get the probability distribution over that because that is the actual new next token that we don't know. And so we want to grab the last token logit. So that's what we're going to do. And then we're going to convert those to the probabilities. And then we're going to look at the top 10 most likely next tokens. The first couple results are reasonably true. The sun does rise in the east in the morning, but GPT-1 is not the smartest model, but west is maybe directionally accurate in some way. Same with sky. Like the model has learned that when this text occurs, the most likely token is somehow related to where the sun is rising. And so that is impressive in and of itself. And so, like I mentioned, ultimately we don't care about this probability distribution. We want to actually pick a token from it. And there's a number of ways to do that. And the techniques here are all called sampling. So how do we pick something from our distribution? And so the simplest approach is greedy sampling. We just want to take the most probable thing at every point. And then there are other things like top K, top P, where essentially we are limiting the space that we're looking at. So in this case, like top K, we're looking at the top 10, and then we could randomly pick from there. And then top P is similar in terms of we're shaping the set that we're going to randomly pick from, but that's a probability rather than a strict 10 number or whatever. And then something I think is really cool is structured generation. So if we have like a true false question that we want to ask the model, maybe that GPT-1 isn't smart enough to actually follow those guidelines, and maybe it says blue is the most likely next token for our question. If we want to guarantee that the model only says true or false, we can simply exclude the entire vocabulary that we pick from. So we have like that 40,000 plus vocabulary. If we just only consider true or false as like valid things to select from, we can take the more likely one from there. And so that's really cool because it's like putting this deterministic rule onto like our probabilistic model. And so if you have a grammar or something like JSON where you need it to follow like a schema, then structured generation can guarantee that your model, when sampling, will only produce valid things. And then temperature is another thing that you'll hear about. And essentially what that does is affect how the softmax scales. So like the higher the temperature, the more creative the model is, because like we can see here, there's a good distance between like the top most likely and the final most likely. And so turning up the temperature would shrink that gap. So maybe all of these things end up around like maybe their average is like zero point 0.2 or something. And so um, if we have a low temperature, the opposite is going to happen. So all of these values would shrink, and then this one would balloon up to like very high. And so temperature affects like what the probability scores actually end up being, and therefore how you can select from them. Um, and so different sampling strategies produce different text styles. So now we understand each piece of this in separation. Let's kind of tie everything together by looking at that transformer pseudocode. So we would have our token embed and then our position embed. And then we'd have our hidden states, which would be a list of transformer blocks for however many layers we have. So this is saying essentially pipe each input through this sequence of 12 transformer blocks. And then ultimately we're going to have that unembed, and then when we actually run this model, we are going to first get the dimension of the sequence length, and we need that so that we can get the position IDs. And then our residual stream, our first hidden state 0, we're going to call our tokens embed and our positions embed and then add those together. And then we're going to run our residual stream through our transformer blocks. And then ultimately we're going to end up with that probability distribution, and then that's what is going to be returned. So going back to our diagram here, now we can understand everything where we convert to tokens, and then we get our token and positional meaning for those tokens. And then that goes onto the residual stream. And then we have many of these transformer blocks where each block has multiple attention heads, which is going to look at the input and do some processing. And then each head is going to take what it learned, and then that's going to end up back on the residual stream. And then that multi-layer perceptron is going to read from there and do further processing, and then back to the residual stream. And then eventually we're going to reach our output stage. So in conclusion, important things for understanding GPT are the residual stream. That really is super important for the model being able to actually do useful things, because the transformer has this shared memory that is always accessible. It's what's read from and written to by every piece of the model, and so that gives it like this working memory where it's able to compute things as it sees most fit. And then mechanistically, that attention mechanism is important because it's able to contextualize across positions. So it's able to understand the difference between when I mention Apple in terms of pie versus Apple in terms of tech company. Those things mean different. Apple means different things in those contexts, and attention is a mechanism that allows us to learn how to contextualize in that way. And then our multi-layer perceptron is going to do that per position refinement. And then that is the GPT model. That really is the core of the thing. And this like paradigm of embedding and then transformer blocks and then an unembedding, this has really proved to be remarkably resilient. This is the same skeleton that like your favorite LLM today still uses. There have been a lot of optimizations and like tweaks to the sub pieces, but the core pieces still remain. And so yeah, I'm going to be putting this code on GitHub, and so you can see the slides there too. Please like and subscribe if you found this interesting or meaningful, and I'll be putting out more content similar to this in the future. Thank you for watching.